This is Chemistry Unit 11, Energy. How much energy does it take to change the states of matter of substances? So far we've looked at solids and liquids in depth. We looked at their intermolecular forces. Gases will be the focus of our next unit. But we have discussed phase changes, right? Like melting, solid to liquid, or evaporation, right? Liquid to gas. How much energy does it take for that to actually occur? Well, let's start by looking at some particle pictures. So let's just look at water, liquid water. So what if we had 6 particles of liquid water versus 12 particles? So here we'll have our liquid water, right? It flows, so they're going to be a little bit farther apart, right? Versus 12. So let's double it. 4, 5, 6, 8, 10, 11, and 12. All right, but now what if we had ice? 6 particles of ice versus 12 particles. So the ice now is going to be more packed together. It's a solid. So here's our 6 particles versus 12. Okay, so the question is, do you think that the mass matters when we change states of matter? So 6 particles of water to 6 particles of ice. So this is freezing, right? Or you could reverse it. 6 particles of ice going to 6 particles of water, which is melting. Okay, versus the 12 particles. So what if you had 12 particles that you were trying to freeze into ice? Or what if you had 12 particles in an ice cube and you were trying to melt that? So do you think that it matters when the substance is changing its phase, how much of the substance you actually have? So do you think it would be easier or harder for 6 particles versus 12 particles to change phases? Well, the answer to that is, yeah, it does matter, right? If you have less of a substance, there's going to be less time spent in a phase change. The more you have of something, the longer it's going to take to change that phase. Now, this should look familiar. This is a phase change diagram or a heating or cooling curve, right? So on the y-axis, you had temperature. And then on the x-axis, we looked at time originally, but here you could have the heat being added. Okay, and what is heat referring to? Heat is referring to energy, right? So now we're going to connect our phase changes to energy. So this should look familiar. Here's the melting and freezing. Here's the liquid and gas, which is condensation or vaporization. And remember this flat line, what that actually meant? There's no temperature change during a phase change, right? Hopefully that looks familiar. And then here are your 3 states of matter. There's the solid, the liquid, and the gas. Now, if a phase change is to occur, it will require energy, which is what you saw on that phase change diagram. And remember, energy is the capacity to do work or produce heat, right? And there are 2 basic types. We have kinetic and we have potential. So I just really need you to know the types, the calculations, I will say for physics class. So if you want to calculate with kinetic or potential energy, take physics. So you can see what physics might be calculating in terms of potential energy, just saying, or kinetic energy. In any case, what's the difference though? You do need to know the difference. So for kinetic energy, that's the energy associated with motion. And if you are curious, the equation is Ke for kinetic energy is 1/2 mv squared. So m will look familiar, that's mass, but v is not volume, v is actually velocity. Again, take physics if you want to know. If you like bio better, then you could say that this cheetah is exhibiting kinetic energy, right? Just saying, because it's running, it's blurred. Okay. Anywho, next one. The other type of energy is potential. So this is the energy of an object due to its position according to the equation PE equals mgh. So m is mass again, and the g and the h are gravity, and then its position or height, you could say. So again, take physics if you want to actually calculate this, and if you like bio better, then you can say that this animal is like scoping out its prey, so it's just kind of chilling there, so it's exhibiting potential energy because it's not moving. All right, so do you need to consider temperature changes in phase changes? Hopefully, you heard me the first time, the answer is no, right? So we're looking at this area right here during a phase change where that line is flat. So if you remember, that's where the substance is essentially fighting itself, right, to overcome its state of matter and transfer into another one. So temperature remains constant during a phase change. But again, we have joules here on the x-axis because now we're looking at the energy component as well. So why do solids and liquids differ in the time it takes to melt them? We're going to focus on that melting, because what does melting involve? A solid changing to a liquid. And if you reversed it, then you would have freezing. Well, why are solids and liquids different from each other? Well, you have to remember that different substances have different IMFs, or intermolecular forces, between the particles. Solids are different from liquids, right? And then there's different types of liquids, different types of solids. And if you remember, the forces were the dipole, the London, and the hydrogen bond. So it takes different amounts of energy to overcome those intermolecular forces between the particles. So you do need energy for solids to be converted into liquids, and vice versa. This has a name, this concept. This is called the heat of fusion, or HF. So fusion is just another term for melting. So it's the amount of energy it takes for a gram of a substance to melt. Okay, and this is something you will not need to memorize. Just like specific heat, substances do have their own heats of fusion. They will differ based on what they're made of, solids versus liquids. So this is something that will be provided to you. You just need to know how to calculate with it when we get to that towards the end of this unit. All right, now how about liquid to gas changes? Does it take a different amount of energy to change different substances into gases? And the answer to that, yeah, sure is. Let's look at alcohol versus water. So just think of like rubbing alcohol or hand sanitizer, right, versus water. Which is more volatile? Does that sound familiar? Which has the greater IMF, or intermolecular force? We talked about this when we were talking about vapor pressure, right, in volatile liquids. So if you remember what volatile meant, it evaporates fast. It's not explosive. It evaporates fast. So alcohol versus water, which is more volatile? The answer is alcohol, right? Just think of hand sanitizer, rubbing alcohol, right? Which has the greater intermolecular force? It would be water. So alcohol would be weaker. Why is that? Water has the hydrogen bond, right? That's the strongest of the three forces keeping that water together. So if you spill water versus spilling rubbing alcohol on a desk or surface, right? The alcohol will evaporate pretty quickly. The water will eventually evaporate. It's just going to take way more time, right? So that means it's got stronger intermolecular forces, and alcohol has a weaker intermolecular force. Okay, so the alcohol turns to a gas faster, so it has the greater vapor pressure. You did learn that. But what I'm trying to get you to connect this to now is that last line. It's called the heat of vaporization. This is the amount of energy it takes for a gram of a substance to be changed from a liquid to a gas. So hopefully you're starting to see now a lot of connections between states of matter and intermolecular forces, energy, and how much you have of the different substances. Okay?